Okay, and we're back here. And if you remember what we were talking about uh, was how the computer worked. We said we had a processor, we had memory, we had these system buses or the wires that connect the processor to the memory. The memory really only just stores numbers. There's some special memory boxes like these ones along here that connect to real world devices like the graphics card, which connects to the monitor, keyboard, the mouse, and the hard drive. And all of these kind of work together. Now, the idea is that the CPU has an instruction, like let's say move. It can take a number and move it out, go out over the buses, grab that number, pull it into one of its registers. It can then carry out another instruction, like maybe move another number out of a box into one of the registers, and then maybe add those two together to produce a result, and then maybe do another move to move those back into some place in memory. So really simple. Again, the CPU, often described as a brain, it's really much more simple than that, much easier to understand that. Just a collection of circuits or machines, you can think of them as, that do each of these simple operations, nothing complex, nothing mysterious, nothing magical about it. So we had finished up with a couple questions. The first one is, where is the program stored? Where where does the program come from? So you notice the CPU has to have these instructions in order to do something. Where does it get the instructions from? How does it know where to move, when to move something, when to add something? And the answer to that is that the instructions are really just stored in memory with everything else. So in other words, in memory, an instruction like move really isn't written as move. It's just a number that represents move. So there are different instructions, different numbers or variants of each of these instructions. Like move would have several different variants. One to move a value from memory into the A register, maybe one to move a value from memory into the B register, maybe one to move A to B, maybe one to move B to A, another move to move from A to memory, move from B to memory, and so forth. So those variants of that are just represented by a number. So, for example, 46 might be an instruction that says add A to B. 47 might be subtract B from A, and so forth. So really, the instructions are stored in memory as numbers. So really simple idea. Now, the second part of this question we asked before we took our break was, where is the data actually stored? So data obviously is stored in memory. So this number here, like 65, that could be representing a quantity of things. It could be an instruction. It could be part of some other pixel value for data. It could be the letter A, capital A. It could be part of a box used together with another memory box to store something. But really, the data is stored in memory. The instructions are also stored in memory. When you look at memory, they all just look like numbers. So the third question we had was, how does memory actually store numbers? So how are those numbers actually stored in those boxes? And that's actually something we'll spend a little bit of time on. So let's go to page 4 here. So this will be page 4. We'll label it. Okay, so how are those numbers stored in memory? Well, let's take a look at that. And it turns out that that's relatively easy to understand, that if we look at the way that those numbers are stored in memory, essentially we can think of memory as this box that just stores a number. But inside of that box, really, the way that the numbers are stored is they're stored as what we can think of as switch settings. So this is a bank of 8 switches. So this is 8 switches. And each one of these can be either off or on, just like if you had a light switch, the light switch could be turned in the off position, it could be in the on position. And these 8 switches together make one memory block, or one byte is what we would call that. But if we look at these 8 positions here, all of them could be off, all of them could be on, some could be on, some could be off. But the idea here is off. Rather than having to write off in all of these and on in all of them, we're going to represent that with 0. And on, which is the other possible state, is going to be represented by, let me make these equal signs, as a digit 1. And that's going to be convenient because it's going to give us this really kind of short way of representing the pattern that we're storing there. It can either be off, it can be on. Now, so if all of these are off, so let's actually fill in that memory box with all of them off. So let's make 8 cells here. So there's my 8 cells. If all of them are off, we would put all zeros in there. So there's my 8 zeros. So all 8 zeros here, we would say that represents the number 0 in decimal. And decimal just means base 10 number system, the number system you're used to using for a lot of the things you do in your daily life. And if we were to turn all of them on, then that has a representation as well. So let's draw that. So if I were to put a 1 in every one of these positions, in all 8 of them, then that represents a decimal number of 255. So in other words, this single block of memory, like we had over here, every one of these single blocks in memory that consists of 8 switches. And those 8 switches could have all zeros, meaning all off, or some of them off, some of them on, in the various patterns. And the highest number you could get to is all 8 of them turned on, which would be a number of 255. Now, that just doesn't quite answer how those numbers are stored. So we're going to kind of expand on this a little bit. And in order to do that, let's kind of go to a new page here. All right, so that was page 4. And actually, before we get away from this 8 switches together, that's what we would call 1 byte, is 8 switches. And each switch, there's another name for each of those switches. So one switch equal 1 bit. So this is an 8-bit block, and 8 bits together as a group are thought of or termed a byte. So in other words, 8 bits equal 1 byte. And we'll come back to those definitions a little bit later on. Okay, so going to page 5 here. All right, so page 5, what we're going to do is we want to dig into how those numbers are stored with a little more detail here. So if you remember, we said that all zeros represented 0, all ones out of those 8 switches represented 255. But the way it works is something like, how do you get a certain number with a certain pattern of bits? Well, let's take a quick look at that. And it turns out that it's something you're already used to. If you're used to decimal numbers, then you're used to the concept of place value. So for example, if I have a number like 243, then you'll notice that each of these places here, each digit, has a place value associated with it. So for example, if we were to write what those place values are, then this is the ones place, ones. This is the tens place, and this is the hundreds place. So the way we make sense of that number is in decimal is through each of those place values. So in other words, if we were to break this out into each of the kind of positions, then the way we'd think of this is that's 2 times 100. So this represents 2 times 100 plus this one is 4 times 10, and then this one is 3, so plus 3 times 1. And you can kind of see that when you read this, 243. So 243. So in other words, this is 200 plus 40 plus 3. So 243. Now, the same concept of what we have there works in the way that those numbers get stored in the computer. It's just that instead of base 10, where the place values are multiples of 10, in other words, to get from 1 to 10, you multiply that by 10, multiply that by 10 to get there. If you want to continue, you multiply that by 10 to get 1,000, 10,000, 100,000, million, and so forth. So binary numbers essentially work the same way. So let's go and write out our 8 bits here. So here's 8 bits. I'll write out a 8-bit binary number here. So there's 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 positions. And let's just stick a number in there. Now that with binary numbers, I remember that since it is a represented by switches, they can only be zeros and ones. So here I'll do like 0, 1, 1, 1, 1, 1, 0, 0. So there's a number, a binary number. It's just a pattern of switches, some off, some on, other ones off. But if we think about those place values again, we can assign place values to these just like we assigned place values to the decimal number. So this is still the ones place. This, though, instead of the tens place, is the twos place because binary numbers are base 2. There's only 2 digits. Notice in decimal there's 10 digits, 0 through 9. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10 total digits there. But in binary, since the switch can only be off or on, there's only 2 possibilities. So it's base 2. So this is the ones place. This is the twos place. The fours place. 8, 16, 32, 64, and 128. So those are the place values. And how do we get a number? How do we know what number that is? Well, we just add up the ones that have 1. So in other words, this is 164. So 0, 128, but 164. So this is going to be 64 plus 132 plus a 16 plus an 8 plus a 4. And then we don't have 0 2s, we have 0 1s, so we just add all of those up. So let's go ahead and add all of those up and see what we get. So to add those up, we'll just do it kind of like the old school way that maybe you would do this in 2nd grade or whenever you do that. So let's just stack them all on top of each other and add it up longhand. So 64, 32. We could add those up and then add the 16 to that, but I'm just going to stack them all up on top of each other. So 16, 8, and 4. So notice there's my 5 1s. I don't have to put the 1 times every time because 1 times that is that. So 64 plus 32 plus 16 plus 8 plus 4. And let's add those up. All right, so to add those up, let's just go through and add them up. So here's how I would do this. I'd say 8 plus 2 is 10. 6 plus 4 is another 10. So there's 20 in that top thing, so 24. So we'll move the 4 down here. Carry the 2 up there. And now we have 6 plus 3. So 6 plus 3 is 9, plus 1 is 10, plus 2 more, 11, 12. So 124. So notice the number 124 decimal looks like this in memory, this pattern of bits in memory. All right, so relatively simple. If you remember, it works just like decimal numbers you used to. It's just base 2 instead of base 10. And that's the kind of key difference here, is that decimal numbers are base 10 And binary numbers are just base 2. But the numbering system works the same way. And a question arises like, well, why do we use binary numbers in the computer? And the answer is, well, because it's easy to make these either off switches that are either off or on. And it would be harder to make a switch that's maybe part way on or part way off, like a dimmer, and then you'd have to work that out. And so it turns out that most computer systems work on this binary numbering system because it's easy to make machines, circuits that actually have switches in them that are either off or on. But the cool thing is, because we have this way of representing those, we can really represent numbers as patterns of those switches. And just because they're represented like this doesn't make them any less of a number than if they're represented in this more human way. Now that does bring up an interesting question. The interesting question would be, why, we know why computers use base 2, because it's easy to represent with switches. But why do humans use base 10? Why did we adopt a base 10 numbering system if it's really the same thing? It works the same way as base 2. I mean, why 10? Why not 11? Or why not 4, 3, or 2? And the answer to that is really somewhat interesting. That it has, like I've asked this question before, and I'll have people say, well, base 10 is easier. And I'm like, well, why is it easier? Oh, it's just naturally easier. And it turns out that that's not really the case. Base 10 is not any easier than base 2. It does create a little more compact representations of numbers, but it's mathematically not any different than what we did over here. It's just these multiply by 2 to get to the next place value, these multiply by 10 to get to the next place value. So the question is, why 10? And the answer to that is actually pretty simple, and it comes from the fact that we happen to have evolved with 10 fingers. And so we tend to look at the world around us in groups of 10 things because we can count them on our fingers. So the idea here is that really this is more natural to humans because we have 10 fingers and we think of things in groups of 10. The computer has the switches, which are either off or on, so it's more natural for it to have things represented in that base 2 system. But you can represent the same numbers. In fact, the decimal numbers that are in a computer are stored in this binary form. We can make it so the computer prints it out or shows it to us and shows it like this. But even if we're showing this like on the screen, like a 2, 4, and a 3, the 2 is represented by a pattern of bits, the 4 is represented by a pattern of bits, and the 3 is represented by a pattern of bits. So the idea there is that inside the computer, there's no such thing as the decimal number 243. It's either individual characters, which each have a bit pattern, or it's just a pattern of bits like that are stored in some byte or group of bytes in memory. All right, so that answers that question. And notice that we now have this way to convert from binary to decimal. You basically just put the place values on top, start with 1, double each time to get the next one. Anywhere there's a 1, we just add those to our list, add them all up, and the resulting value becomes our decimal representation of that same pattern of bits. And pretty easy to understand, relatively straightforward. Now, one of the things that comes up is sometimes, though, is what happens if we want to store a number larger than can fit in 0 to 255? Like if we have to store, I don't know, 256 or 1,000. And the answer to that comes in, we just use more bits. We just use multiple bytes together. So 2 bytes together allows us to have this larger range because now we have 16 bits instead of just 8. And so notice with a single byte, we can store a number in the range 0 to 255. With 2 bytes, or that's 16 bits, we can store a number in the range 0 to 65,535. So the idea there is that because this doubles each time as it moves across, we can just have 2 bytes that work together to store larger numbers. And when you're talking about the difference between, let's go back to this computer drawing we had over here, back on page 3, where you talk about like a 64-bit architecture or processor versus a 32, that's really how many of these are sent together across the system buses, or how many bits wide is the system bus. So a 32-bit computer will move 32 bits at a time from memory. In other words, 4 bytes at a time from memory across those wires into the CPU. And the CPU has the capability of storing those 32-bit wide numbers in there. If we have a 64-bit machine, it'll move 8 of these at a time, and it'll have registers and an architecture inside that can handle 8 bytes at a time, or 64 bits. And that's really why a 64-bit architecture is faster, because it's moving twice as much data at the same time. And there are 8-bit microprocessors or 8-bit systems. For example, a lot of the old arcade machines and the original Atari 2600 and the Nintendo NES systems, those were all 8-bit systems. There are 16-bit systems, obviously 32-bit, 64-bit systems. So really it's just how much memory are we pulling out at one time to move into the CPU and moving back each time. Now, one other thing that's important to note is we already talked about how in memory that we have instructions and data all stored together, and that data could be in the form of it could be ASCII values, a pattern of bits representing a character. It could be a number like we have here with this number 124. But ultimately all memory is, it's not really storing numbers, it's not really storing letters, it's not really storing colors or sounds, it's just storing patterns of switches like we see here. And those can either be used to represent instructions or numbers like we have down here. But it's all just patterns of switches. So again, the computer system, very simple, doesn't know what it's doing, doesn't have any concept of like thinking or reasoning. It's just carrying out an instruction that moves a pattern of bits into the processor, performs an operation that produces a new pattern of bits based on what kind of operation it is, and then moves that pattern of bits back into memory somewhere. Okay, so relatively straightforward. And one of the things that I kind of want to finish up with here today, this will be a relatively short lecture today, is I want to do one more example of converting from a binary number into a decimal number to show the place values. And then I want to talk a little bit about the how do you store like fractional numbers, because this only does whole numbers. There's no fractional space here. And it turns out that that's really easy too. So let's finish up with one last page here. Do one more example of a conversion, and then we'll look at how you could store a fractional number. So this is page 6. Okay, so let's do one more example. So let me draw my 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. So there's my 8-bit position. So let me put a number in here. 1, 0, 0, 1, 1, 0, 1, 0. Okay, so there's my number. And so that's what's being stored in memory. Now we want to know, that's in binary or base 2. What is it in decimal? So what's the decimal representation of that same number? Okay, well, how did we figure it out before? Well, we assigned the place values to each of those. So let's go ahead and write those above it. So 1's place, and then next to that is the 2's place, and then the 4, 8, 16, 32, 64, 128. It's an 8. Now, we just need to add up the ones where there's a 1. So it's the same as 1, 128. So this is 128 plus no 64s and no 32s, but 116. So plus 16 plus a single 8 plus no 4s but a 2, and then no 1s. So we just need to add these up. So let's do that like we did before. Stack them up. So 128, 16, 8, 2. All right. So here, 8. I guess what I would think of this as 8 plus 8 plus 6 plus 2 is another 8. So 8 plus 8 plus 8. So that's the same as 8 times 3. So 24. So put the 4, carry the 2. So 2 plus 2 is 4, plus 1 is 5. So 5, nothing carries, so 154. So that number up there is 154 decimal. All right, so pretty straightforward, pretty simple. Just write the place values and put that there. Now, the question is, though, what about fractional numbers, like 0.5? And it turns out that there's a special format for storing those fractional numbers that kind of works the same way as this, but notice that you could have a decimal point in this. Let's actually draw that out here. So I'll put it down here. So if we think of those place values in decimal, when you say like 1.53, let's do 11.53. Notice that there's place values associated with things on the left of the decimal over here, and there's things on the right of the decimal. So if we were to write the place values for that, and let me put a line here showing that this is a different section. That notice that this is the ones place, that's the tens place, but over here, that's the tenths place. That's the 0.1s place. This would be the hundredths place, or 0.01s place. Well, the same thing is true for binary. We can do that same kind of concept in binary. So this is saying we have 1 10 plus 1 1 plus 5 tenths plus 3 hundredths. And that's how you get that 11.53. Now, in binary, it works the same way. So let's take a binary number and do the same thing. So remember, we had our 8 positions, 1, 2, 3, 5, 6, 7, 8, but I could put a decimal point, and I could put digits after that decimal point as well in binary. So over here, I could say, well, let's just fill in all zeros here. We'll say 0, 0, 0, 0, 0. Let's do 1, 1, kind of like we had over here, but this is 10, not this is decimal, not binary. And then let's put a 1, 0, 1, 1 over there. Now, what number is that in decimal? Well, let's put the place values on there. So the place value on this, that's the ones place. This is the twos place. Now, these are all zeros, so I'm going to leave those off. But this one on the other side of the decimal point, you remember in decimal, it was the tenths place. But here, this is going to be the 1/2 place. The next one over is the 1/4 place. Next one over is the 1/8 place. And just to do this, here's 4, here's 8, here's 16. The next one over is going to be the 1/16 place. But notice it's the same pattern we had going this way as over here. Just like over here, this tenths place is 1 over 10. That's 1 over 100. The next one would be 1 over 1,000. So it really is the same method. Now, in the computer, the way that the decimal values are stored is they're stored in this 32-bit block, or 4 bytes block that's 4 bytes long. And then it's a thing called floating point, where it stores the pattern of bits, and then it has another set of bits that determines how far the decimal place is moved across that pattern. And we're going to look a little more carefully at that later and what the implications of that are. But just note right now that there's nothing magical or easy or special about the decimal numbering system. Binary works the same way. It just so happens that binary can be easily mapped onto computer hardware that uses switches to store those things. And we're going to come back and look at this more later, but kind of what I would like you to do is have the ability or get used to the idea of doing those conversions. And I also want you to get used to the idea of the kind of terminology. A bit is a single switch. 8 bits makes a byte. 2 bytes together makes what's called a word. 4 bytes together makes what's called a double word. And that terminology, or getting comfortable with that and thinking about the fact of how many bits that is or how many switches that is going to be fairly useful to you. And we're going to look a little more at that next class. So we're about at the half-hour mark now for this, which is what I wanted to get through today. We will come back and look at this a little more later and talk in a little more depth. We're also going to spend a little more time on these number conversions. We might have a little quiz on that at the end of next class. But for now, we'll go and stop there, and we will continue on next time. So stay safe, and I'll see you soon.